Look out into the night. Beyond the familiar glow of cities, beyond the veil of our atmosphere, you are staring into an abyss of bewildering scale, a celestial expanse so vast that the light from its farthest shores has traveled for more than 13 billion years to reach your eyes. Within this tapestry are the constituents of everything we have ever known: planets, stars, galaxies, and the incandescent clouds of gas that birth them. This is what we call normal matter. It is baryonic matter, the protons, neutrons, and electrons that assemble themselves into the atoms of our world. It is the substance of you, of me, of the earth beneath our feet, and of the most distant star we can perceive. We have grown quite adept at taking a census of this material. Our telescopes, like celestial accountants, tally up the light from galaxies. Our spectrographs analyze the shadows cast by interstellar gas. We have built a ledger of the cosmos, a grand inventory of everything, and when we add it all up, a terrifying, profound mystery emerges, a discrepancy so immense it challenges our understanding of the universe itself. Based on our most fundamental theories and our clearest look at the dawn of time, there should be twice as much of this matter as we can currently find. Half of the universe's normal matter, half of everything that should exist, is missing. It is not simply hiding in dark corners. It has vanished from the cosmic balance sheet. This isn't dark matter, that separate, enigmatic substance that haunts galaxies. This is the ordinary stuff, the material of existence unaccounted for. For decades, we have searched for this lost cosmic treasure. We have hunted for it in the cold, dim spaces between the stars and in the tenuous, sprawling halos that surround galaxies. We have found some of it, but not enough. The books remain unbalanced. The question echoes in the silent halls of astronomy: where did it go? The answer, it seems, is as dramatic as the mystery itself. It was not misplaced. It was not lost. It was violently, cataclysmically, and systematically taken. The culprit is the most extreme, the most powerful, and the most voracious object in all of creation. The thief that stole half the universe is the black hole. To comprehend this profound absence, we must first travel back in time, not merely decades, but millennia, to the dawn of human curiosity. Ancient observers saw the sky as a dome of fixed points of light, a celestial clockwork of predictable divine motion. The inventory of the cosmos was simple: the sun, the moon, 5 wandering planets, and a spray of unchanging stars. This was the entirety of reality. Then came the telescope, a simple instrument of polished glass. In the hands of Galileo, it shattered the celestial sphere forever. He revealed that the hazy band of the Milky Way was not a celestial cloud, but an uncountable multitude of individual distant suns. The universe suddenly became deeper, more populated, more complex. Our cosmic inventory expanded dramatically. Centuries of refinement followed this initial breakthrough. Larger and more powerful observatories were constructed. They revealed swirling nebulae, cosmic nurseries where new stars were being born, and the ghostly remnants of stars that had perished. Yet everything we saw was still believed to be contained within our own galaxy. The Milky Way was, for all intents and purposes, the entire universe. This conception was obliterated in the 1920 seconds by Edwin Hubble. From his perch on Mount Wilson in California, he studied those faint, fuzzy nebulae. He discovered that one of them, Andromeda, was not a cloud of gas within our galaxy. It was a galaxy in its own right, an island universe, as they were called, composed of hundreds of billions of its own stars, and it was millions of light years away. The cosmos did not just expand, it exploded in our consciousness. Our single ledger became one of millions, then billions. The universe was filled with galaxies, immense spinning disks of stars and gas, all racing away from each other in an ever-expanding reality. This was the universe we set out to catalogue. The method of this cosmic accounting is a masterpiece of indirect detection. We measure the light emitted by stars and galaxies, a straightforward process. From the brightness and color of a galaxy, we can estimate its stellar mass. But stars are only part of the story. Much of a galaxy's normal matter exists as vast clouds of hydrogen and helium gas, the raw fuel for future star formation. This material doesn't shine brightly on its own. So how do we weigh a substance that is largely invisible? We look for its shadow. Astronomers use a clever technique involving the light from even more distant objects like quasars, which are hyperluminous galactic cores. As the light from a background quasar travels across billions of light years, it passes through the intervening clouds of intergalactic gas. Atoms within those clouds absorb specific frequencies of light, leaving a unique, barcode-like fingerprint in the quasar's spectrum. Each dark line in that barcode tells us about the composition, the temperature, and the density of the gas the light passed through. It is like analyzing the sunlight filtering through a distant, unseen forest. By observing the leaves, we can deduce the nature of the trees. For decades, we used these methods, counting the bright stars and reading the dark absorption lines to build our map of all there is. We meticulously added up the mass of all the galaxies. We calculated the weight of all the detectable gas clouds between them. The numbers grew, the picture became clearer, but a sense of unease began to settle in. The universe felt emptier than it should. The confirmation of this cosmic deficit came not from looking at the universe today, but from peering at its infancy. The key was a faint, ever-present glow of radiation that bathes the entire cosmos. It is called the cosmic microwave background, or the CMB. This is the afterglow of the Big Bang itself, the very first light released when the universe was just 38,000 years old. Back then, the cosmos was a hot, dense, opaque fog of plasma. As it expanded and cooled, electrons and protons finally combined to form neutral atoms. This event, known as recombination, allowed light to travel freely for the first time. That ancient light has been traveling ever since, stretching to longer, cooler wavelengths as the fabric of space itself expanded. Today we detect it as a faint microwave hum in every direction we look. It is the universe's baby picture. And encoded within this photograph are the universe's deepest secrets. The CMB is not perfectly uniform. It is mottled with infinitesimally small variations in temperature. These tiny fluctuations, mere fractions of a degree, represent the seeds of all future structure. The slightly denser, slightly cooler spots were the gravitational wells from which the first stars and galaxies would eventually form. By studying the precise pattern and size of these spots, we can determine the exact recipe of the early universe with stunning precision. Spacecraft like COBE-WMAP and the Planck satellite have measured these patterns. Their data gives us the initial budget of the cosmos. It tells us that the universe at its birth was composed of roughly 5% normal baryonic matter, 27% dark matter, and 68% dark energy. That 5% is the crucial number. It is the cosmic standard, the amount of material we are supposed to have. The CMB provides an unambiguous, authoritative figure for the total amount of baryonic matter that must exist today. Because normal matter, unlike dark energy, is conserved, it cannot simply vanish. And here the paradox solidifies into a crisis. When our cosmic accountants take the CMB's initial budget and compare it to their census of the modern universe, the sum of all the stars and all the detectable gas, the numbers do not match. They don't even come close. Our modern inventory can only account for about half of that 5%. Somewhere between the universe's infancy and its current sprawling maturity, we have misplaced a quantity of normal matter so vast that it is equivalent to trillions upon trillions of Earths. It is enough material to build a whole second universe of galaxies. This is the missing baryon problem, and its existence sent shockwaves through the astronomical community. The hunt was on. Theorists and observers scrambled to propose and then test potential hiding places. Perhaps the matter wasn't missing, but merely difficult to see. One of the first ideas was that it was locked up in dim, compact objects. Maybe the halos of galaxies were filled with countless brown dwarfs, failed stars, not quite massive enough to ignite nuclear fusion. Or maybe the universe was populated by rogue planets, ejected from their solar systems, drifting silently in the cold dark. These hypothetical objects were collectively known as MACHOs for massive astrophysical compact halo objects. Detecting them directly was impossible, but their gravity could in theory betray their presence. According to Einstein's general relativity, mass warps space-time. If a MACHO were to pass directly in front of a distant star, its gravity would act like a lens, briefly and characteristically magnifying the star's light in an event called gravitational microlensing. Ambitious surveys were launched monitoring millions of stars for years on end, waiting for these telltale flickers. A few events were found confirming the existence of such objects, but there were nowhere near enough of them. The microlensing results were stark. MACHOs could only account for a tiny fraction of the missing mass. The bulk of the universe was not hiding in dim, compact bodies, so the search turned elsewhere to the space, times between times the galaxies. Cosmological models had long predicted that the universe should be structured like a colossal three-dimensional spider's web. Galaxies are not scattered randomly. They are clustered along immense filaments of dark matter like pearls on a string. The junctions of these filaments are home to massive galactic clusters, while the spaces in between are vast dark voids. Perhaps the missing baryons were not in the bright galactic cities, but spread thinly along these intergalactic highways. This concept gave rise to the idea of the warm-hot intergalactic medium, or the WIM. The theory was that this material left over from the formation of galaxies would be heated by shock waves and gravitational collapse to temperatures of millions of degrees. But it would also be incredibly diffuse with only a few atoms per cubic meter. Detecting such a tenuous hot plasma is extraordinarily challenging. It is far too thin to emit much light of its own. To find it, astronomers had to return to the shadow technique, searching for its absorption signature in the light of background quasars. But because the gas is so hot, its atoms are stripped of most of their electrons. This makes them very poor absorbers of visible light. The search had to be conducted in higher energy wavelengths, like X-rays. Using sensitive space telescopes like the Chandra X-ray Observatory and XMM Newton, astronomers painstakingly scanned the skies. After years of effort, they found it. Faint, ghostly absorption lines from highly ionized oxygen and other elements precisely where the cosmic web filaments were predicted to be. This was a monumental discovery. A significant portion of the missing matter had been located. It was indeed lurking as a hot, nearly invisible fog in the spaces between galaxies. But even this was not the complete solution. The WIM, as best as we could measure it, seemed to account for perhaps 30 to 40% of the missing total. When added to the matter in galaxies, our cosmic inventory was still short. We were still missing a final substantial piece of the puzzle. A profound amount of material was still unaccounted for. The hunt had led us through the galactic halos and into the cosmic web, but the mystery endured. There had to be another process at play. A mechanism powerful enough not just to hide matter, but to fundamentally redistribute it on a cosmic scale. And for that, we have to turn our attention to the shadows. to the gravitational monsters that lurk at the heart of every major galaxy, the supermassive black holes. Imagine a tranquil, wide river flowing across a vast plain. The water represents the primordial gas of the early universe, the baryonic matter destined to form stars and galaxies. As the river flows, gravity causes small eddies to form. These eddies are the nascent galaxies, swirling pools where the gas begins to concentrate. Within these pools, smaller glittering specks begin to shine as the gas condenses into stars. This is the visible universe we can easily account for. Now imagine that at the very center of each and every major eddy, a powerful, unseen drain opens up. This drain is a supermassive black hole. Its gravitational pull is relentless, drawing in a significant portion of the river's water. This material, once it crosses the event horizon, is gone forever from our view. It has been consumed, effectively removed from the visible universe's ledger. This is the first part of the solution. Black holes directly devour matter. The amount of matter locked away inside every supermassive black hole is substantial, but even this isn't enough to solve the crisis. The real story is not what falls into the drain, but the unimaginable violence of the process of it falling in. As the water spirals faster and faster towards the drain, it doesn't just slip in quietly. It forms a chaotic, brilliant, superheated vortex. Friction and magnetic fields within this swirling disk of water, the accretion disk, heat it to incandescent temperatures, causing it to glow brighter than the entire rest of the eddy combined. This is the quasar phenomenon. Now, the crucial part of our analogy. The energy released by this violent vortex is so immense that it creates a powerful upward pressure, like a geyser erupting from the drain itself. This geyser blasts a huge amount of the incoming water, not down the drain but back out of the eddy entirely. It launches this material far away from the river, flinging it as a fine, superheated mist across the entire plain into the empty spaces between the main currents. This ejected mist is so thin, so hot, and so widely dispersed that it becomes almost impossible to see. This is the grand mechanism. The feeding frenzy of supermassive black holes in the early universe did not just consume matter, they powered colossal galactic winds, tsunamis of plasma that erupted from the centers of young galaxies. These outflows, driven by the intense radiation of quasars, were so powerful they blasted a significant fraction of a galaxy's baryonic gas completely out of the galaxy's gravitational grasp. They launched it into the deepest, darkest cosmic voids. This is where the last of the missing matter went. It wasn't just hidden in the filaments of the cosmic web, it was violently exiled into the near-total emptiness between them, spread so thinly that it became a cosmic ghost. The black hole didn't just eat part of the universe, it took the rest and flung it into hiding. This idea, known as black hole feedback, has become a cornerstone of modern astrophysics. It is a process of cosmic self-regulation, a delicate and violent dance between creation and destruction. In the early universe, galaxies were forming rapidly. Vast quantities of cold gas streamed from the cosmic web into their gravitational wells. This provided the fuel for furious bursts of star formation. It also provided a feast for the nascent supermassive black hole at the galactic center. As the black hole grew, its accretion disk blazed with the light of 1 trillion suns. The radiation pressure from this quasar became an unstoppable force. It began to push against the very gas that was trying to fall in. Simultaneously twisted magnetic fields in the accretion disk acted like cosmic particle accelerators, seizing some of the infalling plasma and launching it outwards as relativistic jets, twin beams of matter and energy traveling at nearly the speed of light. Together, these forces created a galactic-scale superwind. This outflow propagated through the young galaxy, heating the remaining gas and halting further star formation. It was a feedback loop. The black hole's growth spurt effectively choked off its own food supply and stunted the growth of its host galaxy. But more importantly for our mystery, it evacuated a tremendous amount of baryonic matter. Computer simulations are our laboratories for testing this cosmic hypothesis. Cosmologists build virtual universes inside supercomputers, inputting the laws of physics and the initial conditions measured from the CMB. They then press play and watch as gravity pulls dark matter into a web-like structure and normal matter pools within it to form galaxies. For years, these simulations had a persistent problem. Without some extra physical process, the simulated galaxies they created always ended up far too massive and forming too many stars compared to the real galaxies we observe. The simulated universe was too bright, too cluttered. The breakthrough came when physicists added the physics of black hole feedback into the code. They programmed the virtual black holes to grow to accrete matter and, crucially, to pump enormous amounts of energy back out into their surroundings. The results were transformative. The simulated galaxies suddenly began to look just like the real ones. The powerful outflows from the black holes ejected gas, quenched star formation, and sculpted the galaxies into the right sizes and shapes. And most importantly, these simulations showed precisely where the gas went. It was blasted far out beyond the galaxy's halo into the intergalactic and intravoid regions. The simulations balanced the cosmic books perfectly. They showed that this violent feedback mechanism was not just a possibility, it was a necessity to explain the universe we see today. But a simulation is not proof. Observational evidence was still required. And finding it has been one of the great triumphs of modern astronomy. Using the Hubble Space Telescope and its sensitive spectrographs, astronomers have caught this process in the act. They have observed distant galaxies with active feeding supermassive black holes, and they can see the clear spectroscopic signatures of immense outflows of gas rushing away from the galactic center at thousands of kilometers per second. We can measure the mass and speed of this escaping material. We have seen the shock waves where these winds slam into the surrounding intergalactic medium. We have even found the smoking gun evidence for the final hiding place. By using multiple quasars whose light paths pass near each other, astronomers can perform a kind of cosmic tomography. They analyze the absorption signatures along each path. If the light from one quasar passes through a cosmic web filament, it shows the expected absorption from the WIM. But if the light from a nearby quasar passes through an adjacent void, it too shows faint but detectable absorption from superheated gas. This is the material that was ejected, the final missing piece of the baryonic puzzle, found exactly where the black hole feedback model predicted it would be. The case was closed. The black holes in their spectacular violent youth had fundamentally re-engineered the visible cosmos. They are not just cosmic vacuum cleaners. They are cosmic architects, shaping the distribution of matter on the largest scales imaginable. So the universe we see is a lie, or rather, it is a carefully edited version of the truth. When we gaze at a galaxy, we are seeing only the material that survived. The matter that was lucky enough not to be consumed by the central monster and fortunate enough not to be exiled by its fury. The emptiness of the cosmic voids is not a primordial emptiness. It is an imposed barrenness populated by the ghosts of matter violently cast out from the bright centers of creation. This revelation forces us to reconsider the role of black holes. They are not merely endpoints of stellar evolution or gravitational curiosities. They are active, dynamic engines that govern the evolution of the universe itself. The growth of every galaxy is inextricably linked to the growth of its central black hole. The number of stars in a galaxy, its shape, its color, its ultimate fate, all are influenced by the ancient tantrums of the beast at its core. What then is the long-term destiny of this missing matter? Is it lost to the voids forever? For some of it, the answer is likely yes. Ejected with such tremendous velocity, it will continue to drift through the expanding void, growing ever more diffuse, never again to participate in the cycle of star birth. But some of it may eventually cool and rain back down onto the filaments of the cosmic web, or even onto the outer halos of galaxies over billions of years, a slow cosmic drizzle of recycled material providing a trickle of fuel for a final sputtering generation of stars. This understanding paints a new, more dynamic picture of our cosmic home. It is a place of constant exchange of dramatic outflows and slow, patient infall. A universe sculpted not just by the gentle pull of gravity, but by the explosive regulatory power of its most extreme inhabitants. The solution to the missing baryon problem is not just an accounting fix, it is a paradigm shift. It tells us that to understand the whole, we must understand its most violent parts. And it reminds us that what is visible, the beautiful spiral arms of a galaxy, the gentle glow of a nebula, is often just the quiet aftermath of a far more tempestuous story. The atoms that make up our bodies, forged in the hearts of long-dead stars, are the lucky survivors. We are made of the baryonic matter that remained behind. Our existence is a testament to a cosmic battle fought eons ago, a struggle between the creative force of gravity and the destructive power of a feeding black hole. As we continue to peer deeper into the cosmos, we will undoubtedly uncover new mysteries. The nature of dark matter and dark energy still eludes us, representing 95% of the universe's total composition. Our triumph in locating the missing baryons is in the grand scheme solving a mystery about a mere fraction of reality. But it is our fraction. It is the matter that matters to us. And in finding it, we have discovered that the story of the universe is a story of disappearance and exile. A tale of how the brightest lights in the cosmos conspired with the deepest shadows to hide half of creation in plain sight. The night sky will never look the same. We now know that for every star we see, for every glowing cloud of gas, an equal amount of its sibling matter was banished to the dark. The universe is a grander, more violent, and more interconnected place than we ever imagined. And at the heart of it all, in the center of every island of light, the culprit still waits silently, patiently, holding the secrets of what was and dictating the fate of what is yet to come, undefined.